let's say that we have a boy that is swinging on a swing set, and at this particular instance, theta is equal to 60 degrees, and he has a velocity of 15 feet per second. He weighs 60 pounds, and we're asked to figure out what the tension in each one of these ropes are, and what his rate of increase in speed is. Well, an increase of speed is just acceleration. So acceleration is equal to his dv divided by dt. So his change in velocity over a change in time. And how do we go about figuring all this out? Well, we really need to start with a free body diagram. And if we draw our free body diagram, we have this boy sitting on a swing, and here's the seat. Here's the rope. And because it's a swing set, he has a rope on each side of him, so this is really 2 times the tension because there are 2 sets of ropes that he's holding on to, one with each hand. His weight is coming directly, oops, that's not good. His weight is coming directly down, and he weighs 60 pounds. And in this particular problem, we are going to say we're going to use tangential and normal coordinates. So this is my normal coordinate and this is my tangential coordinate. We're doing this because he's moving on a curved path. So this is equal to some kinetic diagram. And if we draw this, we're going to say that this boy has some acceleration in this normal direction. So here's our normal direction again, and he's going to have some mass times acceleration. And since we're given his weight is 60 pounds, his mass is going to be 60 divided by g, and g is going to be equal to 32.2 feet per second squared. So we know that because we're in English units. So he has this mass times a normal acceleration, and he has this mass times a tangential acceleration. So we're going to say that there's an acceleration in the tangential direction. So it's his mass, 60 divided by g, times the acceleration in the tangential direction. So now let's sum our forces in the tangential direction and sum our forces in our normal direction. We'll start with the tangential direction. And we have right here, well, we have to figure out what this angle is. We know that this right here is 60. So this is a 30-degree angle. You can prove that with geometry, but this is a 30-degree angle. And so his force in the tangential direction becomes the sine, right? It's this way. So he has 60 times the sine of 30 is equal to a mass, and his mass is 60 divided by g, times the acceleration in the tangential direction. And this right here, we have all the pieces of information because we know what g is. G is 32.2. We can evaluate what his tangential acceleration is, and his tangential acceleration is 16.1 meters per second squared. So this is the rate of change, and we were also asked to figure out what the rope of this tension, what the force in each of these ropes are. And in order to do that, we have to sum our forces in our normal direction. So for sum of the forces in the normal direction is equals a mass times the acceleration in the normal direction. And up is positive, so we have 2t. Down is negative, so we have minus 60 times the cosine of 30. and this is equal to a mass, so 60 divided by... Sorry about that, my pen just stopped working for a second, but it's equal to 60 divided by g times the acceleration in the normal direction. And we have two unknowns. We have this normal acceleration, which is unknown, and we have this t, which is unknown. And we're trying to solve for t. However, we do know that a normal acceleration is equal to a velocity squared divided by rho. And rho is our radius of curvature. Yes, I forgot to give this radius of curvature again for the second video. This radius of curvature is 10 feet. So we do have enough information to solve this problem. If we try to figure out what this normal acceleration is, we have our velocity at this point, which is 15 squared, over our radius of curvature, which is 10. We have a normal acceleration of 22.5 meters per second squared. And we can substitute this in right here. So we have 2t minus 60 times the cosine of 30 is equal to 60 over g times 22.5. And when we solve, we get the tension in each of the ropes is equal to 46.9 pounds.